Hi guys! In today's video we're going to be talking about drawing gradient functions. So far, every time that we've found a derivative or gradient function, we've done so mathematically, using first principles or later using the rules to shortcut the process. What is also possible though is to determine the nature of a gradient function directly from the graph of the original function. Cases where we might use this process include if the equation of the original function was unknown, or if it was of a form that was difficult to differentiate, so we didn't have a rule to shortcut the process. So let's take a look at an example. What we have here is some arbitrary function, f of x, and we want to be able to work out what its gradient function, what its derivative is going to look like. So let's start with what we know. We know that the gradient function, the derivative, f dash x, is a record of the changing slope of the original function. So what we do is we go and look at the function and we see what its slope was at different points. So in this first section, the slope is up. Then for a while, it's back down again. Then it's back up, down, and up again. Now, in between each of those places is a point where the gradient of the function becomes zero momentarily, where the function stops going down or up and then reverses direction. Each of those points will have a gradient of 0. So we can put all of those on our graph. And we know that in between, the gradient was either positive or negative. So we already have an idea about what this function will do. In this first part, we know that the gradient is positive, then it's negative, then it's positive again, then it's negative, and then it's positive. And that will correspond to the actual values that we see in our gradient function. So the gradient function will have to start positive, go through 0, go negative for some short time. Now we can see that it doesn't go very negative because the line is almost flat the entire way. Then it goes fairly positive before turning back over again, coming back through that point that we know is 0, and then doing the opposite, going negative, then back up, and in the end it looks like it's just going positive. And there we go. That is a sketch of what our gradient function looks like. And we can do more things later to add more detail to that and make it more accurate. But in the meantime, it's given us a pretty good idea of what the gradient of this function is doing at any point. We know the points where it crosses through 0. We know the points where it has a large positive or a large negative gradient. And we can find those points, if we want to, where it changes. So we can find maxima and minima as those points where it's going to be 0. We can find the maximum slopes as the points where the gradient has the maximum positive or negative values. So all of that information is kind of there for us even without a function. We'll quickly look at one more example just to make sure that we've got all the concepts. So here we have our function f of x, and we can see that it initially rises before going flat and then rising again, but asymptoting off to y equals 0. At every point in this function, the gradient is either positive or 0. The graph never drops. So when we go to draw our derivative function, we have to keep these features in mind. So we start with a fairly positive gradient that drops down to 0 around this point here, where it's flat. Come down there, but then it starts rising again. It doesn't actually pass through, it doesn't turn over. It gets to 0 and then turns back up until about here, where it starts to flatten off again. But it never quite reaches 0. It asymptotes. So the function is getting closer and closer to the x-axis, and therefore the slope is getting lower and lower, but it never quite reaches 0. And so what we're going to see is behavior that also asymptotes in the derivative, with the slope getting closer and closer to 0, but never actually quite reaching it. So that's a really weird function, the way it behaves. It kind of drops down to 0 before rising, coming up and then turning back over and asymptoting out towards 0. Another interesting thing about this function is that the function itself is always negative. It never rises above the x-axis, whereas the derivative is always positive. It's never negative. And that's a really important point, because those two things can often be disconnected like that. The function might be always positive but have negative gradients, or always negative but have positive gradients. And so don't judge the value of the gradient based on the value of the function, whether it's high or low. Remember that we're only ever looking at the shape, how it's sloped, to work out the derivative.